Hello everyone, this is Professor Ma and this is the sections the looking for real roots. Okay, um, in last sections we have theorems about how real polynomials can factor what's a complete factored form of real polynomial looks like. It look like this. A bunch of linear polynomials which give you the real roots and there are a bunch of second degree polynomial give you complex. Okay. Now, then we come down to the practical problems. How do we find real roots? And that is pretty much a very difficult question to answer. Okay, and what we are going to do is we're going to give you different flavors of, in this section, we're going to give you three different angles about how we go about it. Okay, and so we're going to talk about the Descartes rule of signs, and basically that tells you how many roots, real roots that you're looking for, the possibility of the numbers of real roots. And the second theorem tells you where will the roots be, within what looking at the coefficients of the formula, you can tell where the boundary of the roots are. And then the third one is we actually say how do we look for fractional roots if the formula is integer polynomial. Okay, so uh, the Descartes rules of and the theorem of the first two method basically doesn't tell you what the roots are, and they just tell you the root if they exist, okay, or if justify they exist. So we call those existence theorems uh, in mathematics. Okay? And theorem of the rational roots, the third one, of course, is something more precise. Tells you if you're looking for these type of roots, these are the only candidates, and either you find them in here or they don't exist. So the answer for that are more precise. Um, okay, first we from the fundamental theorem of algebra, the way it breaks down, and so these part of the roots are all even power. Okay, so if the power of polynomials are, then there must exist at least one of these type, which means there must be at least one root. Okay, so that's what this theorem is basically over here. We start out with observation. So if polynomials are degree, it must have at least one real root. Okay. Now, I'll come to the Descartes' rule of signs. Okay, so talk about that. We first talk about the variation of signs of polynomials. You know, the variation means how many times it change, flip-flops. So if I look at a polynomial, I look at the signs, the orders of signs from the highest degree term down to the coefficients, and I write them down. Then the variation of the signs is how many times it change. So in this case, the variation is 2. Okay. And Descartes' rule of sign tells you it tells you how many positive roots are there. Tell you how many real roots could possibly be there. Okay. So we have a real polynomial. Then the number of positive roots, okay, is equal to this variation of sign. It's equal to, in this case, it's equal to 2 for the positive roots in this polynomial is equal to 2, or less than that by an even number. So it could be 2 real roots for this problem because variation of sign is 2. There could be 2 real positive roots. or it could be 0, be less by an even number. Okay, two less than 2 is 0. So it could be 2 positive ones or no positive. And how do we check for negative ones? Well, if we put minus x, plug in minus x, and we check for minus x, the negative roots, negative or negative is positive, that will turn into the positive roots for p of negative x. So we do the same thing for check the variation of signs for p of negative x. Okay. Then we get equal to or less than the variation of signs by the even number. Okay. So the variation from the last slide, we have we concluded there could be 2 positive roots or no positive roots. Okay, and we plug in minus x, and then there is switch all the negative terms. I mean, sorry, the odd power terms into the negative of the opposite. Okay. The even one, of course, stays the same. And then we count the variation of sign for this one. We see these are 3 sign switches. Hence, the number of negative roots could be 3 or 1. Okay. So from these 2 pieces of information, I can classify how many possible positive roots, negative roots, and so on, so on. There must be. Okay. Could be the following 4 different cases. Right? I could have 1 negative root and no positive, no other negative. Then you would have 2 irreducible for the second degree port, the other part, the longer part, and those become the 4 complex roots. And I could have all the other cases. Okay. And for example, I could have all 3 negative roots. Okay, 3, and I could have the 2 positive roots. Okay, that's another possibility. So think about all these different possible cases. Now, theory of bounds tells you if you're looking for real roots, where will they be? And it's very simple. Suppose this is the polynomial. The theory of bounds says you take the first number, you divide into everybody, divide with that, all the coefficients, and look at these divisions and pick out the biggest one. Okay. And look at this biggest number coefficient, divide by the first number, then add 1 to it. So for example, if I list the coefficient of this polynomial, the biggest one 6. So take then the biggest number, divide by the first number, which is 2. Okay, an means the very first numbers, and then add 1 more to it, which is 4. And it tells you the real roots for this polynomial must be between 4 and minus 4, somewhere in there. So don't look for it outside 5 or 6 or 7. Now, and one practical use for this is when I do graphing. Suppose I want to say graph. Before that, if the coefficient an is 1, then this particular check, you just look at the largest coefficients plus 1 more. So here, let's go back to suppose I want to find the real roots. Okay, now how do we do this now numerically? Usually this is done on calculator. Okay, so if I want to do it on calculator, where should I plot so I can kind of trace where the roots are? Well, from what we just went through, all the roots must be between minus 4 and 4. Okay, so therefore, I'm going to set the range between minus and 4, and 4 to capture all the roots. And then I'm going to set y to be, say, 20 minus 20. Okay, play around with that. And there they are. Okay. In particular, it shows 3 roots. That's 2 positive roots and 1 negative root. Okay. And so this is how we solve using a calculator polynomials of low degree, okay, by tracing. Then we ask first for integer coefficients. Everything's integers, and then if we break up into parentheses factor, then we usually get a fraction answers, right? So when do we get what kind of fractional roots we will have? Okay. So here we go. And so for the list of possible fractional roots, we make the list in the following manners. Okay, we look at the number A. Okay, and then we look at the coefficient, the constant term B, and then we list all the factors of A and all the factors of B. Then the fractional roots must be these. Here, examples. 6 and 4. Okay. Well, the answer is minus 3 over 2. And notice that minus 3 is a factor of that, and 2 is a factor of the 4 of the front terms. Okay. And similarly, if I look at this and I notice the denominator, okay, for the roots, they are factors of 6 of the front terms, and then the minus 2 and 1 are factors of the constant terms. Okay, so in other words, all the possible fractional roots are the following roots. Okay, for this one, I list the factors of possible factors of 3. And then I list all the possible factors of the first coefficient, 2, which 1 and 2. Then I make all the fractions of B over A. So it is 1 over 1, 1 over 2, 3 over 1, 3 over 2. There's a 4 of them. Then they could be plus or minus. Okay? And this is a complete list of candidates for fractional roots for integer. The polynomial with integer coefficients. Okay. Now, which one it is, and then we check it. And now, in present day, it's very easy with a calculator. You plug it in to see which one comes out. Okay. Now, so let's we use these to factor this polynomial completely. Okay, and let's just assume we play around with it. We finally find out one root. 3 over 2. Okay, then I can use the synthetic divisions to factor this root x 3 over 2 out of the equations, and the synthetic division goes through, we'll get zeros as a remainder, of course. And of course, in this part is the second degree equations. This is the quotient. So now we take the quotients and we factor out the 2, and I take the 2, multiply to make it look better in the front factor. I write as 2x minus 3 if you want to. Okay. Then how do we factor that? Well, we can only use these reducibles, or factoring to using quadratic formula, factoring the 2 real numbers. So this for this factor breaks, this polynomial breaks down into 3 real factors. Okay, so this is how we guess fractional answer, then pick out, check which one fit, and once we find out which one is a root, we factor, make it simpler. Then we look for the roots of the simple ones, and we keep doing these. Hopefully, we can factor the polynomial completely. Okay, so that's it. And that's do the homeworks. Until next time. Bye bye.